Slab analysis and design can be performed by meshing slab using finite element shells. This method can be used for all types of slab, but it is essential for irregular and flat slab system. There are two choices of slab analysis. Building analysis with slab meshed. Tick includes slab and building model. This will assume a full 3D analytical model from top to bottom story. Hence, inherent 3D effect of multiple stories is included. Gravity and lateral load effects can be obtained. The other option is finite element floor analysis. The analysis considers a subframe of one story only. It is fast and simple as analytical model is only one story. Secondary 3D effects of other floors are ignored. Only gravity load can be obtained, that is, no lateral load analysis. Click Slab Strip function in Modeling tab. Ensure to choose FE strip as type in Slab Properties. Span strip is for slab supported by beams. Fixed band strip is for flat slab, with no beams. Analysis result source, pick either, building analysis, or FE floor analysis. Ensure slab strip start and end boundary condition is set correctly. Click and drag the slab strip across slabs to be designed. Do this both horizontally and vertically, that is, orthogonal direction. Run building analysis or FE floor analysis according to the chosen source option. Go to Analytical Model to examine the slab strip and contour results, example moment contour. Use slab analysis and design function to generate rebars and design report. Note, slab strip can also be created after analysis, provided nothing has changed to invalidate the analysis. Let us build a simple model as illustration. Start a new model, say FE slab. Choose Eurocode Singapore template, OK. Click on Orthogonal Axis Generator. Use the defaults to generate 4 horizontal and vertical axes with 5 meters spacing each. Firstly, create a simple tabletop model. Create 4 columns and 4 beams with default sizes. Click on slab icon and click OK to generate the load cases and combinations. Use all the defaults, OK. Then insert slab with 150 mm depth. With 30 mm cover. Dead load of 1 kN per meter square. Life load of 5 kN per meter square. Then, create another tabletop flat slab model without beams. Create 4 columns with default sizes.
Then slab, with 200 mm depth, with 30 mm cover.
Dead load of 1 kN per meter square. Life load of 5 kN per meter square. Click on Slab Strip icon. Start with direction X. Since we want to use the finite elements slab design method, change type to FE strip. For finite elements strip, there are 2 types, namely span strip and fixed band strip. Span strip is the alternative to moment coefficient method, by meshing of slabs. Span strip must pass through slabs supported by beams or walls. Example, 1 beam at the left side, then 1 slab, then 1 supporting wall at the right-hand side. Span reinforcement is calculated according to maximum moment found in span zone, as shown in the above diagram. Support reinforcement is calculated from support moments found in support zone, as shown in the above diagram. Select span strip, since we will be cutting the slab strip for the beam slab model. Analysis results source. Choose building analysis. This means that we must choose to mesh the floor slabs during building analysis. FE floor analysis is the other option, which is a different analysis method that only considers one floor at a time. Boundary conditions. Slab. The strip starts and ends inside a slab. User must specify the length of the slab where the strip ends. The support top bar will extend into the last slab. BOB bending of bar. The strip starts and ends beyond an edge beam or wall. The support steel at the end will bend down into the beam or wall. Cantilever. The strip starts or ends beyond a cantilever slab. Boundary condition at start and end must be chosen correctly, otherwise, slab design will be erroneous. If boundary condition has changed, example, due to change in slab layout, existing slab strip must be deleted and recreated. Choose bending of bar for both the start and the end, since the tabletop model starts and ends with beam. Place the mouse cursor at the left-hand side of the first beam. Click and move the mouse cursor to the right. Hold down Ctrl key to snap to horizontal. Click at the right-hand side the beam. The FE slab strip will be created. We need to cut the strips orthogonally to obtain design both in X as well as Y direction. Change the direction to Y, change number to 1. Cut a vertical strip from bottom to top. No rebars are shown as we have not run building analysis. Now, move the plan view and focus on the right flat slab model. As this is a flat slab, we cannot use the span strip. We must use the fixed band strip. The fixed band strip is specifically for the design of flat slab, raft, or mat foundation. Width of the strip is defined by left extent and right extent input, as shown in the left diagram above. A single arrangement of top and bottom rebar will be designed. It will cover and extend to the entire length and width of the strip, as shown in the right diagram above. Top rebar is calculated based on the maximum negative moment detected in the entire length and width of the strip. Bottom rebar is calculated based on the maximum positive moment detected in the entire length and width of the strip. In the slab strip properties, choose X direction. Under FE strip, choose fixed band strip. Under Analysis Result Source, pick Building Analysis. Boundary conditions is not applicable for fixed band strip, hence it's gray out. The extender scope by default is 1 meter left and 1 meter right, giving a total of 2 meters width. Integral option allows design moment to be averaged. This diagram shows a typical bending moment diagram at the flap slab and column interface. By default, the maximum nodal moment will be used for the FE fixed band strip design, example right at the peak at the center line of column. The integral option will average the design moment across the width of the strip. As such, the wider the strip, the lower the average design value, especially at the column support region, where the moment changes abruptly. Hence the user should carefully evaluate how wide to create each strip when integral is checked, otherwise, the design may be too unconservative. Place the mouse cursor at the left side of the slab. Click and move the mouse cursor to the right. Hold down Ctrl key to snap to horizontal. Click at the right side the slab. The FE slab strip will be created. No rebars are shown as we have not run building analysis. The strip width does not cover the entire slab, hence, only the design moments within the boundaries of the strip will be used. In a real flat slab project, it would be more reasonable to cut several strips of different width, example different strip at column and span area. However, for simplicity, we can adjust the width of the strip to cover the entire slab, so the design will take into account the entire boundary. We can manually key in the left and right width. Alternative, we can automatically adjust the width by clicking on the arrow icon. Then click on the top edge of the slab. Notice left value will auto-update. Similarly, click on the arrow icon again, then click on the bottom edge of the slab. The right value will auto-update. Click Update and the width of the slab strip will now extend to edges of the slab. We will not check the option of integral strip, since the width of the strip is very high and averaging the design moment will be too unconservative. We need to cut the strips orthogonally to obtain design both in X as well as Y direction. Change the direction to Y. Cut a vertical strip from bottom to top. Similarly, adjust the left and right width of the slab strip. Click Update and the width of the slab strip will now extend to edges of the slab. Close the slab strip property dialog. We will now run building analysis. Go to Analysis tab. Click Building Analysis. Click Edit Material. Click Steel Grade of Slabs. Click Edit, next to Rebar Diameters. Review the diameters of bars, to be used for the design of slab. Check or uncheck diameters, to be considered in the slab design. Click OK, OK, OK. Go to Model Options. Slab Model. By default, include slabs and building model is unchecked. This means that the slabs will not be considered or included in building analysis. Since we have chosen to design the slab using finite element method, we must check this option, so the slabs will be included by meshing of the slabs. Click Stories to be meshed, and tick Story 1. Use decomposed slab loads and meshed stories, should be unchecked, in analyzing model which consist of flat slab system, transfer slab system and irregular slab system. Since there is a flat slab, we must untick this option. Include column sections in FE model allows rigid perimeter of the column to be considered. The slab will be meshed to the perimeter of the column, rather than the center line. Ticking this option will introduce more meshing complexity, so let's uncheck this option for simplicity. Shell element size. The mesh uniformity can be controlled by specifying different minimum and maximum shell size. The objective is to have a minimum of 8 to 10 slab meshes between columnar supports. Let's input 800 mm as minimum. Slab stiffness coefficients. In plane, membrane, for slab shells. If checked, this option can simulate semi-rigid floor diaphragms. This mainly affects lateral load analysis. Bending stiffness, out of plane for slab. According to certain concrete design publication, it is common practice to take into account crack and creep effect of concrete slab by decreasing the slab stiffness. Kindly refer to the Prota Help Center for more details on these slab model options. Go to Analysis. Click Building Analysis. Then click Building Analysis. After Analysis, the summary will appear. Click OK. Close the Building Analysis dialog. Click on Analytical Model, Building Analysis Model, because we have chosen to run Building Analysis. The Analytical Model view will open. The functions of Analytical Model are covered in detail in the tutorial video titled Post-Analysis, Analytical Model. Kindly go through that tutorial first, as we will only cover the functions related to slab analysis using finite element meshing method. By default, the displacement of all the elements is shown in red in the Result tab. Let us deactivate this first. The analytical model is what gets analyzed, and where results can be displayed. As you can see, the columns and beams are idealized as single-line frame elements, and the slabs are meshed into triangle shells. If you hover the mouse cursor on any beam, the beam label, frame number and node number will be shown. Similarly, if you place mouse cursor on the slab shell, go to the Members tab, under Frame Members icons, click Frame Load, and Frame Load Labels. This will switch on the loads and values on frame members, which are columns, walls and beams. At the right side is the Load Cases and Load Combinations pane. Since G-load case is selected, the diagram is showing all the dead load calculated on the beams on the left model. This is the self-weight of the beam. The weight of the slab is not calculated on the beams because we have chosen not to use decomposed slab loads in meshed story in the modal options, slab model inputs. Hence the slab shells loads are automatically applied onto the slab itself. The right side is the flat slab model, so there are no beams and hence no frame loads are shown. Turn off both frame loads and frame load labels. Under the shell member icons, you can switch on or off shell information. Example, turning on and off thickness. Turn on pressures. This will be the pressure in kilonewton per meter square on each slab shell element. This is G-load case, which includes the self-weight of the slab, as well any other dead load on this slab. Select Q-load case. You can verify by hand calculation whether these values shown is reasonable. Turn off the pressure.
Turn off the thickness.
Let us now look at the result. Go to the Results tab. Select G-load case. Turn on displacements. The displacement is shown in red lines for G-load case. Click Animation for better visualization. Turn off bidirectional animation to show deflection in the direction of applied loads. Check displacement under each load case, including the pattern load case Q, P. It is very important to check and verify whether the displacement is reasonable, otherwise, the analysis forces will be in doubt, as the deflection of a member is a direct reflection of the forces it experiences. Turn off the animation. Units of displacement can be changed by going to Settings Center, Unit and Format. Under Displacement, change unit, millimeters. Click OK. You can show actual displacement values by clicking X, Y, Z, or R equal resultants. The legend is as shown. At the bottom box is shown the maximum displacement. You can click on it, and an arrow will appear to identify the node with maximum displacement under the selected load case. Turn off the displacement. For a standard structure, we should proceed to examine the member force diagrams. We have already covered this in previous tutorial, hence, we will skip this for now, as our focus is on the analysis and design of the slab.